Let's take a look at gas laws. And if we're going to think about gas laws, we need to think about pressure. Now, pressure is force per area on a surface. But really, when we say that, we mean that it's the force perpendicular to the surface per area. So if I imagine an area A here and a perpendicular force F here, then the pressure is defined as the force per area. So the unit of pressure then has to be Newton per square meter. This is also said to be a Pascal, PA. And if we think about a gas, when we think about gas pressure, the reason why there is a gas pressure is because the molecules in the gas impact some surface, maybe the side of the container. So let's imagine one little molecule and it hits the side of the container. When it bounces off, it applies a force to the wall. And if we have many, many molecules, all impacting the side, some of them straight on, some of them more of a glancing blow, the total force that they all apply per area is the gas pressure. So obviously, we're going to be talking about many, many molecules when we talk about gases. So we're going to need a way to discuss large numbers of gas molecules. We need a way to easily discuss large numbers. And because of that, we're going to define Avogadro's number. Avogadro's number is 6.02 times 10 to the 23 per mole. So Avogadro's number is the number of individual particles per mole. And remember, a mole is this thing that we use that is a number of other things. It's a convenient way to talk about large numbers. And Avogadro's number tells us how many things there are per mole. So if I have 10 moles of protons, say, then that means that I have 10 moles times 6.02 times 10 to the 23 per mole. So I have 6.02 times 10 to the 24 protons. Or if I have half a mole of hydrogen atoms, well, I have half a mole times 6.02 times 10 to the 23 per mole, which means that I have 3.01 times 10 to the 23 hydrogen atoms. So we have this relationship between number of moles, the number of particles, and Avogadro's number. And here it is. N is equal to N over N, which sounds ridiculous when you say it out loud. But this small n over here is the number of moles. This capital N here, that's the number of particles. And the N on the bottom, Na, is Avogadro's number. Now let's talk about the gas laws themselves. The gas laws were observed hundreds of years ago. They were patterns that were noticed by scientists, but they were not explained at the time. They didn't have the idea of the molecule, and they didn't know about atoms at the time. So we're going to look at these four gas laws. First is Boyle's law. Boyle's law is that the gas pressure of a gas is proportional to 1 over the volume of the gas for a fixed mass of gas at a constant temperature. Another way to say this is that the pressure is inversely proportional to the volume. Then there's Charles' law. Charles' law says that the volume of a gas is proportional to the temperature of the gas for a fixed mass of gas at a constant pressure. Then there's the pressure law, also known as the gay-lussac law, and this is that the pressure of a gas is proportional to the temperature of a gas for a fixed mass of gas at a constant volume. And then there's Avogadro's law, and that is that the number of moles of gas is proportional to the volume of a gas for a gas kept at a constant pressure and a constant temperature. So all of these observations that scientists made hundreds of years ago, we can combine them. An expression that combines all of these ideas together is that the pressure of a gas times the volume of a gas divided by the number of moles times the temperature of a gas is equal to some constant. And just as an aside, in your data booklet, you get the expression that PV over T is equal to a constant, which is true as long as the mass of the gas is fixed. But anyway, going back to our expression, PV over NT is equal to a constant. It turns out that the constant that this is equal to is called the gas constant, capital R. This is a constant that's given in your data booklet. It's equal to 8.31 joules per mole per Kelvin. So we can rearrange this now. If we do, we get that PV equals nRT. It's called the equation of state for an ideal gas. Sometimes it's also called the ideal gas law. Now I want to point out that constant there, that R constant, that's actually only true for an ideal gas. And this expression here only applies to an ideal gas, but it's a pretty darn good approximation for a real gas in many situations, as long as the intermolecular forces are negligible. Because remember, an ideal gas, we've seen that before, but an ideal gas is an approximation that we use where we assume that there are no intermolecular forces between the gas molecules until they collide. And previously, when we saw ideal gases, we had an expression for the average kinetic energy of a molecule in the gas. The average kinetic energy of a molecule of ideal gas is equal to 3 halves Kb times T, where Kb is Boltzmann's constant and T is the temperature of the gas. Now, we can take the ideal gas law, or the equation of state of an ideal gas. We can take PV equals nRT, and we can rearrange it a little bit. If we do that, well, let's see. N is equal to N over N, right? So we can replace little n with capital N over Avogadro's number. And then we get this expression, and then we can rearrange it over here, right? Okay. And if we do that, this R over Avogadro's number, that's a constant divided by another constant. And it turns out, if we have that expression, that constant divided by that constant is another constant. It's Boltzmann's constant, which we just saw in that previous expression for the average kinetic energy of a molecule of an ideal gas. So Boltzmann's constant is equal to the ideal gas constant divided by Avogadro's number. So we have another expression, another way to write the equation of state for an ideal gas. PV is equal to nKT. Now, this one, keep in mind, this N is different than the N in PV equals nRT. In PV equals nRT, the N is the number of moles. In PV equals nKT, that N is the number of molecules. And you get the combined expression in your data booklet.